Hi everyone. Today I am going to start with a new paper for the BSc 6th semester. The title of the paper is Polymer Chemistry. In that, the first unit is kinetics of polymerization. So under that kinetics of polymerization, I am going to discuss with mechanism and kinetics of step growth polymerization in this session. Before going to discuss with the mechanism and kinetics of step growth polymerization, it is much needed to recall some terms associated with the polymer chemistry. The first one is polymers. What is meant by polymer? It is very simple. Polymers are macromolecules composed of large number of much smaller molecules called monomers, which can be represented by this schematic diagram. Here I have taken a green beads which represents a smaller molecule called monomers. They combine together to give a very big molecule, a macromolecule, which is called a polymer. So this can be better understood by considering a particular example. Here I have taken polypropylene, which is formed by a monomeric unit, what we call propylene or simply propene. So it is CH2 double bond CH CH3. See this CH2 CH CH3, it is a repeating unit which repeats itself to give a very big molecule, what we call polymer. So the process of converting monomers into polymer is called polymerization. In 1929, W.H. Carruthers suggested a classification of polymers into two groups based on the mode of polymerization involved. So that mode of polymerizations are addition polymerization and condensation polymerization. Later, Fleury emphasis on the mechanisms by which the two types of polymers are formed. So based on the mechanism, the polymerization process can be classified into step growth polymerization, which is also called condensation polymerization, and chain growth polymerization, which is also called addition polymerization. So in this session, I am going to discuss with the step growth polymerization, the mechanism and kinetics of step growth polymerization or condensation polymerization. Let me consider that. Step growth polymerization. The polymer buildup proceeds through a reaction between functional groups of monomers in a stepwise manner. The chain growth is not spontaneous and usually occurs slowly. In case of step growth polymerization, the monomers first form a dimer, then a trimer, then a tetramer like this. The long reaction times are necessary in order to reach polymers with a high average molecular weight in case of step growth polymerization. So the monomers which are involved in the step growth polymerization may be of the type AB or AA bar BB. Let me consider first case. The monomer which is involved in the step growth polymerization is of the type AB. That is, a monomer is bifunctional. The functional groups are different, which is represented by A and B. So this monomeric unit, which in turn combine with another one monomeric unit to give a dimer, which in turn combine with one more monomeric unit to give a trimer. Like this, a long polymeric chain grows in a stepwise manner. Let me consider a particular example. Here I have taken amino acid. It is having two functional groups, NH2 and COOH. So one unit of monomer will combine with another unit of monomer to give a dimer, which in turn combines with one more unit of monomer to give a trimer. Like this, the polymer chain grows. As it is a condensation process, it involves the elimination of small molecules like water. Here, the three monomeric units combine to eliminate 2 water molecules. Now let me consider another case, the condensation process, which involves the monomers of the type AA and BB. Here I have taken two different monomeric units. So this monomeric unit is a bifunctional, which is having two functional groups at the end. The functional groups are similar. It is also having two functional groups, the same functional group at the end of a monomeric unit. So this one monomer represented as AA will combine with a BB, which in turn combines with AA, and then it combines with BB. Like this, the polymeric chain grows. So have a look at this example. Here I have taken a monomer. This is adipic acid and this is ethylene glycol. This is monomer having two functional groups, AA, that is COOH, here also COOH. It is BB, here it is OH and OH. So these two are combined with the elimination of water molecule, then which in turn combine with one more molecule of adipic acid and one more molecule of ethylene glycol. So like this, the polymeric chain grows along with the elimination of water molecules. Now, how does this polymerization process proceeds? So that is what we are calling mechanism of polycondensation. So for that, I am taking an example of a polymerization between two different monomeric units, that is AA and BB type of monomers are involved in the polycondensation. Here I have taken ethylene glycol and adipic acid. They combines together and eliminates a molecule of water to give this product. So the product so formed, which is having a reactive groups at the end. Here it is OH and COOH. So it will combine with one more molecule of adipic acid and one more molecule of ethylene glycol, like this. See, I have taken this product obtained from the first step. It is made react with one more molecule of adipic acid and another molecule of ethylene glycol, and it gives a somewhat bigger molecule. So this step can be simply represented like this. So two molecules of adipic acid combines with two molecules of ethylene glycol and gives this molecule. So if I say, if more quantities of ethylene glycol and adipic acid are made available, it is capable of forming even a bigger molecule. If there are n molecules of ethylene glycol and n molecules of adipic acid are available, they will react together to give a very big molecule, what we call polymer. So it can be simply represented like this. So n molecules of adipic acid combines with n molecules of ethylene glycol and it produces a big molecule, that is what we call a polymer. This is how the polycondensation reaction proceeds. The polycondensation reactions may be of two types. The first one is self-catalyzed polycondensation and the second one is acid-catalyzed polycondensation reaction. So now I am going to consider the kinetics of both the self-catalyzed polycondensation and acid-catalyzed polycondensation. Let me consider the first one, kinetics of self-catalyzed polycondensation. Here I am taking the same example that I have considered while explaining the mechanism, that is the adipic acid, n molecules of adipic acid made react with n molecules of ethylene glycol to give a polymer. For an uncatalyzed reaction where the diacid and diol are present in equimolar amounts, one diacid is experimentally found to act as a catalyst. See, this point is very important. In case of self-catalyzed polycondensation, one diacid is experimentally found to act as a catalyst. The reaction is followed by measuring the rate of disappearance of carboxyl groups. So which can be represented like this. The rate of disappearance of carboxyl groups, that is minus d by dt of COOH concentration, it is equal to K into concentration of COOH to the power 2 and concentration of OH. In general, the self-catalyzed polycondensation reaction is followed like this. Rate of polycondensation, it is equal to minus dA by dt, it is equal to K into concentration of A to the power 2 and concentration of D to the power 1, where A represents the concentration of acid and D represents the concentration of diol. So when A is equal to D, the concentration of A is equal to concentration of D, then we can write it as minus dA divided by dt, it is equal to K into A to the power 3. Then you rearrange this equation, you will get dA divided by minus of dA divided by A to the power 3, it is equal to K into dt. You just integrate this equation over the limits. A is equal to A naught to A is equal to AT, that is concentration of A at the time 0 and concentration of A at the time t. So you will get 2 kT is equal to 1 over concentration of A to the power 2 plus an integration constant. Then you apply the limits. 2 kT, it is equal to 1 over AT to the power 2 minus 1 over A naught to the power 2. You call it as equation number 1. It is convenient to express this equation in terms of extent of a reaction. So it is like this. So AT is equal to A naught into 1 minus P, where P is defined as the fraction of functional groups that have reacted at time t. Thus 1 minus P is the fraction of groups unreacted. Then you substitute this equation 2 in equation 1. So you will get this expression 2 kT is equal to, here it is 1 divided by AT to the power 2. You substitute the value of AT, that is A naught into 1 minus P. It becomes A naught square into 1 minus P whole square minus 1 divided by A naught square. Then here 1 divided by A naught square is common. You take it out, then it becomes 2 kT is equal to 1 divided by A naught square into 1 divided by 1 minus P whole square minus 1. Then you cross multiply this. 2 into A naught square into kT is equal to 1 divided by 1 minus P whole square minus 1. Then you rearrange it. You take minus 1 to the left hand side, it will becomes plus. Then you rearrange it. 1 divided by 1 minus P whole square is equal to 2 into A naught square kT plus 1. You call it as equation number 3. A plot of 1 over 1 minus P whole square as a function of the time t should then be a linear with the slope A naught square into K, from which the K is determined. Now you look at this graph. It is a plot of the self-catalyzed polyesterification of adipic acid with diethyl glycol at 166 degrees Celsius. As I mentioned, this should be a linear. But in fact, the linear portion corresponds to only a relative narrow range of conversion. Roughly, it is from 80 to 93%. Deviation at lower conversions are attributed to change in the polarity of the reaction medium as the monomer are converted to a polymer, and the deviations at higher conversions to an increase in the rate of reverse reactions. Then the number average degree of polymerization, which is represented by dPn bar, can be expressed as dPn bar, it is equal to number of original molecules divided by number of molecules at a specific time t, which can be represented like this. Number of original molecules is n naught, number of molecules at a specific time t, let it be n. So for this particular equation, it will be A naught divided by AT. So thus degree of polymerization, average degree of polymerization is equal to A naught divided by AT. You substitute the value of AT here, A naught divided by A naught into 1 minus P, A naught gets cancelled, then it will be 1 divided by 1 minus P. You call it as equation number 4, and this equation number 4, that is number average degree of polymerization is equal to 1 divided by 1 minus P, is called Carather's equation. From equation 3 and 4, it can be seen that, see, for equation 4 is here only, you consider the equation 3, that is 1 divided by 1 minus P whole square is equal to 2 into A naught square KT plus 1. So this 1 over 1 minus P is called as number average degree of polymerization according to equation 4. You substitute the value, then it becomes number average degree of polymerization to the power 2, that is equal to 2 KT A naught square plus 1. In this expression, the degree of polymerization appears to be second power and time appears to be first power. Hence, the polymer molecular weight will increases only slowly in case of self-catalyzed polykondensation. Now you consider the kinetics of acid-catalyzed polykondensation. So for that, I am considering the same equation. So in case of acid-catalyzed polykondensation, the condensation reactions are enhanced by the presence of a strong acid as a catalyst. For a catalyzed reaction where the diacid and diol are present in equimolar amounts, the reaction is followed by measuring the rate of disappearance of carboxylic acid, which is simply represented as the rate of disappearance of carboxylic group minus d by dt of COOH, that is equal to K into concentration of COOH into concentration of OH. In general, the acid catalyzed polykondensation can be represented like this: minus dA divided by dt is equal to K into concentration of A into concentration of B, where A represents the concentration of acid and B represents the concentration of diol. When A is equal to B, the concentration of acid becomes equal to a molar concentration of B. Then we can write it as minus dA divided by dt is equal to K into concentration of A to the power 2. On rearranging this equation, you will get this expression: minus dA divided by A naught square is equal to K into dt. Then you integrate this equation over the limits A is equal to A naught to A is equal to AT. So you will get this expression: KT is equal to 1 over A, concentration of A, plus an integration constant. Then you apply the limits. KT is equal to 1 divided by AT minus 1 divided by A naught. You call it as equation number 1. Again, it is convenient to express this equation in terms of extent of reaction. So it is like this: AT is equal to A naught into 1 minus P. So where P is defined as the fraction of functional groups that have reacted at the time T. Thus 1 minus P is the fraction of groups unreacted. You call it as equation number 2, and you substitute equation 2 in equation 1 and rearrange. So this is what the equation 1: KT is equal to 1 divided by AT minus 1 divided by A naught, that will be equal to 1 divided by, substitute the value of AT, it is there in the equation 2, A naught into 1 minus P minus 1 divided by A naught. 1 minus A naught is common, you take it out. So KT is equal to 1 divided by A naught into 1 divided by 1 minus P minus 1. Then you rearrange this equation: A naught into KT is equal to 1 divided by 1 minus P minus 1, or we can rearrange to get 1 divided by 1 minus P is equal to A naught into KT plus 1. So a plot of 1 divided by 1 minus P as a function of time should then be a linear one with a slope A0 into K, from which we can determine the value of K. So you consider this plot. So it is showing a reaction of ethylene glycol with adipic acid, and this reaction is catalyzed by para-toluene sulfonic acid. See, it is almost a linear one. Then the degree of polymerization for the acid catalyzed polycondensation, that is equal to dPn, that is number average degree of polymerization, that is equal to A0 into Kt plus 1. According to this equation, degree of polymerization appears as the first order and time as the first order. Hence, the polymer molecular weight build up in this case will be faster when compared to the polycondensation reaction without catalyst. So far I have explained about the step growth polymerization, that is polycondensation reactions, the mechanism of polycondensation, and the kinetics of two different polycondensation reactions, that is self-catalyzed polycondensation and acid-catalyzed polycondensation. Hope you understood them. Thank you.